Thank you to organizers. This is a wonderful event. First time for me here, and I should commit to join in the next few years. Yes, so today I'm going to speak about challenges in quantum software and possible open source solutions. I'm a CTO at Unitary Foundation and also managing the European entity we have. So let's start straight on with what I believe are challenges in quantum software, but I would say quantum computing more in general. But of course, software is involved. So the first challenge, we heard it from previous speakers too, is compilation. So strictly speaking, how do we program quantum computers in not a naive way? So in ways that are scalable and noise resilient. How do we enter this early fault tolerance stage era with all the related constraints? Second challenge is benchmarking. We heard it a little bit already, but let me tell, basically we want to answer the question, what is the best quantum computer right now? How is this evolving over time? What is the best computer or program practical on a computer for a given application? And more generally, I would also say, how fast is the field progressing? Because there is like a need to report to stakeholders, policymakers, and society as a whole about the rate of progress of the field overall. Then I also find the third challenge, which is hardware development. So has the best qubit chip and design, or even qubit technology, been designed already, or we need to discover new ones, invent new ones? And what is the role of academic research at the time of the quantum industry, where you are literally, if you wish, working, if not competing to some extent, at least at journal level, publication level, with companies that are focused and have a lot of resources to optimize things. And also I would say HPC and QC, how do we put these things together? And finally, something that we really care about at Unitary Foundation, it's a community growth. And how do we develop and attract talent also from other areas? And maybe something is more specific, but I think it's important. How do we ensure national or regional strategies, it could be like EU level, are equipped efficiently with respect to what is being done in other parts of the world and relying on what is the best talent already developed throughout the years? Okay, this is about what we should actually aspire to, but let's now talk about the proper challenges, a bit high level. It's been already said more in detail at the compilation level by the talk by Lucas, I would say. It was great. But there's a lot of duplication with SDKs. There's even what I would call even camps for different solutions in intermediate representation or compiler frameworks. And we really need to have tools that are cross-platform, scalable, and error resilient. And then on top of this, we need to add the fact that, again, noise, it's really detrimental. Quantum error quantum error mitigation cannot do it all, but I'll argue that it's here to stay. And this brings some other challenges. And then for quantum error correction, we heard it a little bit earlier. There's really a lack of tools for quantum error correction, because the stack has so far been designed only for the near intermediate scale quantum computing time. For benchmarking, benchmarking is fragmented. There's a duplication also there. And generally, I would say there's a lack of cross-platform benchmarks. There's a bit of this Hartree law where there's this pet metric that maybe a provider is chasing, and then the different providers are fighting with each other because their metric doesn't, say it's better than the other ones. And so we really need independent evaluations there. And for hardware, I would say, what is challenging right now is that it can be expensive and bureaucratic to access computers on the cloud. I think it's great that there's industry players that have really committed a lot of resources to make the community grow and learn how to use their devices, also help them develop the ecosystem. I think there's also need to be this redefinition of what it means to do quantum computing research in academia. And then, again, we need to develop talent and vibrant community. But this is a fantastic event that shows that this community is already growing and it's here. So let me mention something that maybe we don't always appreciate, and I think it's something we should cherish and also protect, safeguard in the coming years. Since what we could call like academic prehistory, quantum computing and quantum technology tooling has been mainly open source. And let's start with QuTiP, a project that really got me into open source, and I'm one of the admins of that very popular quantum optics toolkit. And then there's been like things like Rigetti, putting a computer on the cloud, Quill, IBM Quantum Experience, QuiZkit, of course, and then this now very open ecosystem environment with a lot of tooling that is being built and a lot of best practices actually being shared across the ecosystem. But here, if we focus on compilation models, I think we really are starting to see that how the system has evolved up to now, it's starting to bring some stiffness. And by this, I mean that a siloed environment, where at the bottom you can imagine having hardware, and on the top some user or applications, really can bring some duplication. Some duplication, it's fair, as it is fair in general in open source, because that also means competition. That also means that, as we know, we don't have something like a Silicon Valley, so we have very different architecture, so it does make sense that we have a very specific tooling for different kind of even hardware architectures. But we should really plan to have more modular architectures, and I really like that Lucas already covered more in technical detail, things like MLIR, LLVM, or frameworks that one can think about. And yes, I'll mention Jeff, which is like an interchange format for compilers. It's something that actually the folks at Xanadu and Quantinuum came to us with, really with this idea that we need to evolve from a quantum circuit representation, that it's like a unitary, with something that has dynamically if conditions and checks and things that you want to do also in this quantum error correcting era, and really start to think in terms of programs. So something like structured representation, efficient compilation, extensible by design, and of course, being able to accept other frameworks, be it from Catalyst, from Ticket, from UCC, which I'll introduce in a second, and share passes, such as optimization passes, and interoperate across the stack. And I'm really glad that as Unitary Foundation, we can host this project, and we would like more folks to contribute to it, really, again, to try to reduce the duplication in the field. One thing that we're developing in-house with the technical staff I lead is the Unitary Compiler Collection, which also in the logo tries to recall GCC, the GNU Compiler Collection, but with a cat, of course. And we want to build a hub for quantum compiler experts to develop new passes, be it transpilation, optimization, reduce the friction between high-level application developers and the simulation and access to hardware, and then continually survey and build the open source ecosystem. And we do it also with support from Department of Energy and National Science Foundation in the US. So what was the wish list that led us to build the compiler UCC? First, there needs to be an alternative to proprietary compilers. Some platform independence from a researcher point of view is fundamental, and also start to adopt consistently language standards. And we're trying to adopt all these features in UCC. So let me really show you a snippet that really shows that UCC is front-end agnostic. You can come with your QuiZkit or Ticket circuit, and then you can just call the compile function here that is being imported by UCC, and that's like the single line of code where you need to use UCC. So UCC adopt customized passes. We started also building on top of QuiZkit, and then fine-tuning some parameters, adding our own passes, and we want to accept new passes. Of course, we need to continuously benchmark how this fares, and we're also preparing for early fault tolerance. So we're also building some tooling, such as UCC-FT, which is a verifier that checks whether a quantum circuit, a quantum program is fault tolerant. And you would be surprised by how little definition in practical terms is there for meaning something like quantum program is fault tolerant. So we're contributing to building this tooling. And in the general stack, I would say this is really middleware that is not really quantum application or quantum algorithm specific, but it deals with error correction management, logical and physical layers, and then doesn't deal with, let's say, the pulse level, at least at this point, part of a stack. And you can see UCC, and you see in this stack also Mythic. And Mythic is a project that actually is now fully integrated with UCC, that can be called by UCC. And it's been it's been the first project that the team at Unitary Labs and Unitary Foundation developed. And it's a cross-platform error mitigation toolkit. So it's really like a thin layer in between the user and the hardware. And again, to some extent, due to the existing duplication that many of you know, we made it compatible with many front ends. But then by design, it's also run on any backend and allows to apply error mitigation passes. For those of you that are not familiar with it, it just means that usually instead of running a quantum program and sort of like use the cross your fingers and hope that what you get is not just gibberish out of it because of noise, you actually sample the landscape of noise in clever ways. They can go from dynamical decoupling. Now, people refer to this as error suppression, but also do some extrapolation once you have all these many programs that are different from one another and from these noisy results. And then you get an error mitigated result. And Mythic has just reached the threshold of 300,000 downloads, almost 90 contributors to this day, several distributions on PyPy, and also like more than 300 pages, if you count them as pages, web pages on the documentation online. So check it out if you haven't yet. And talking about quantum error correction, let me also give us a sneak peek of the survey that we run every year. I believe this is like the third or fourth year we run it. And we asked a pool of developers, more than 1,000, if for quantum error correcting technologies that you would like to use but are not currently using, what are the main reasons for not currently using them? And I think what really strikes me is that the tool does not exist is very high as a reply, it's like actually the highest reply. And this just, in my opinion, is an example of the fact that I was saying that we need to build more tooling. So of course there is the duplication that we need to harmonize, but there are also a lot that needs to be built, especially for the logical layer of things. And then I'm not gonna speak about HPC in this talk, but the only part I'm gonna introduce here is the answer to this question. Do you use software for high-performance computing in your quantum workflows? And 60% of the folks said no. And I think that there's a lot to build. There is actually exciting opportunity because HPC has a long-standing tradition of open source frameworks, but I think that these communities are quite disconnected at this point. If you want to check the 2024 results, please have a look. And there's like very nice and interactive, and you can go through results on the website. Now back to UCC. Maybe I don't know if we can turn down these lights next to the screen. Maybe they're a bit, they can improve the visibility. Let me also mention, it was mentioned in the previous talk, we consistently benchmark UCC, and actually I'm really glad to say that the team set up a continuous integration so that for each pull request, these plots get generated. And here you can see UCC, Ticket, Qiskit by default, Circ, and even things like PyQPanda, which is distributed on PyPy but is not technically open source because you cannot see what they do behind under the hood, are benchmarked against some standard circuits. And you can see how they fare, and we can claim that UCC is doing better on some others, but I think it's really important a message like it's important to have this benchmarking. So let me switch to benchmarking as a topic from compilation, but also like focusing on hardware benchmarking. I think we have the opportunity to provide a framework for reproducible, reviewable, and independent quantum computing benchmarks, and create a community hub for quantum computing benchmarks with involvement of experts, of course, but also like more users. And these will definitely help quantum computing as a field as a whole to bring more clarity about the speed of development and even innovation. So we actually started in 2021, 2022 with this metric project which is the first crowdsourced open platform for quantum computing benchmarks. It's a website, metric.info, and it provides the opportunity from everyone to submit a result, and then extract from that result, from that paper, for maybe like an archive URL, a data point, as you see here from quantum volume, and automatically generates these nice charts. It was built on top of papers with code, so we're also taking like best practices and tooling from the machine learning community, and even informed by the HPC benchmarking community. So the wins has been that this been like the largest database to date in benchmarking, more than 1,600 results, iterative improvements in the UI UX, and we also have like resource estimation sections. As this one that maybe you need to squint to look at, but actually not only benchmarks that have been taken on hardware, but also estimates of what would take on this plot that is logical qubit, this logarithmic plot versus logical operations, like how far are we with respect to factoring or other kind of like benchmarks and applications. But we also found some challenges, and it's very hard to harmonize the taxonomy. And researchers and quantum industry providers, QC providers, don't always have an incentive to do systematic benchmarking. They usually want to get a new paper, they have a nice new research idea. And still, like, you know, we found some challenges in like harmonizing all these taxonomy in the UI UX. So now we have a metric in a new phase, which is still in beta, which is in order to harmonize these results, we cannot just parse what benchmarks people are taking out there, but we need to provide the code, and we actually provide a platform that people can contribute code to, so that this can be then experimentally checked. So we're building this tool. It's a runner, and this runner is now integrating a web platform, and we hope that this will help, will make a community contribute to it and flourish. So the new phase of metric is really this runner, which is called the metric gym. Then, of course, we have the data, which is a data set, and then the presentation, which will still be an online presentation. And you know, the runner is really focused on protocol definition. The data, of course, that's the taxonomy, but also the raw data of the results taken from the benchmarks. And then the presentation will have the sort of like table or graphs that you've seen that are interactive. How does this work? A user uses a schema definition, let's say for quantum volume. We want the community to be involved, so we also help set up an open quantum benchmark committee, but we also would like folks to contribute to and use the framework, even if they're like no gatekeeping. And then this is sent, it's in part of Metric Gym. Metric Gym then dispatches this job to the cloud providers with like all these orchestrator. You can poll the result, and then you can publish on metric.info. And thanks again to the volunteers from the Open Quantum Benchmark Committee. They come from all over the place, Europe, US, Asia, and really are helping provide expert know-how into what the specific benchmark should look like with respect to simulators, compilers, hardware, or even error correction. And really the idea is like to advise on the project, but also empower researchers and developers with open source tools to navigate this quantum benchmarking landscape. So Metric Gym is open, transparent, and cross-platform and user-friendly. But let me mention what we have already in Metric Gym, and we would like to add more. And if you have benchmarks that you're coding or you care about, we would like to consider adding them. So we have a Bell state pairwise checker on qubit chips. We have a wormhole-inspired teleportation check. We have other systemic benchmark like mirror circuits or error per layered gate. But we're also integrating more application-oriented benchmarks, such as this QML kernel or a linear ramp QAOA test, or even QEDC benchmarks. And we're working on Clifford decisions, and we also would like to hear about folks' ideas on logical qubit benchmarks. So how does it work in practice? It's very simple. It's like it's a Python runner, but you really basically use it from the command line. You do something like mgym job dispatch. In this case, the benchmark is the Bell state inequality, so bsec.json, minus provider, IBM, minus device, IBM Sherbrooke. And that's what's there. So of course, the JSON file contains metadata that tells what the benchmark looks like. And you can also do some other actions such as polling, viewing, or uploading the result. From a software infrastructure point of view, this command line calls the benchmarking core, and this interfaces with QBraid. So really thankful to the QBraid team for the work they've done to make it easier to access all these providers. But there's a lot of work that you need to do under the hood to make it work for each provider. And then when we talk about cloud providers, you also want to make sure that this works with device providers. So now we support AWS, which itself supports IQM, Rigetti, and IonQ devices. So you see here at least 2 different modalities. The IBM platform, Nexus, which is like a Quantinuum platform, and also like a Chinese provider, superconducting provider, OriginQ. So we would like to integrate with more. So if you're a quantum provider or a cloud provider and would like to add your integration, please talk to us. Okay, now switching gears and speaking about hardware. And as I mentioned, there is an opportunity to leverage open source software to give more equitable access to hardware, cheaper and faster lab development for experiments, and unleash creativity. Just because the new qubit, the next qubit that really performs better may not have been invented yet. And right now, I think that there are like these sort of like players, industry players, national schemes, and research institutions like HP centers are the ones that are gonna hold the open access on the cloud or some sort of like access with credits. And it's very important that, in my opinion, national schemes and also like community schemes get built up. There's a QuTiP example managed by Oak Ridge National Labs in the US. Horizon had just now like a call to start to build this tech. It's really important to allow users worldwide to access these computers. But then there's like a deeper level with respect to what we can do with hardware, which is like how we can design new kind of hardwares. And I think it's like last week, Arduino got acquired by Qualcomm. And so somehow there is also a way to make money out of open source, as people were asking earlier, because the Arduino project, just like Raspberry Pi, are examples of open hardware in the classical world. And what does it mean to have open hardware in quantum technology? There is many examples. One that I want to mention is this firmware plus software of RF system on a chip developed by QuIC. And QuIC is a quantum instrumentation control kit. It supports experimentalists in the lab working initially with superconducting circuits technology, but is now supporting many more labs and hundreds of labs worldwide. And we're really glad that we're helping this project as Unitary Foundation flourish. So from the open hardware perspective, let me mention that, strictly speaking, open hardware may refer to design of a chip, such with tools like PyEPR that do like finite modeling, KQ circuits, which work at the mask level, leveraging the K-layout, which is also a framework that comes from the classical world. But it also means providing access with foundries, and also installation and bring up, as I mentioned, with QuIC. All this is what I refer to as open hardware. If you want to learn more, we have this review that we written a couple of years ago. And as Unitary Foundation, we support open hardware in many ways. We give catalyze these processes with communities. We're giving some micro grants to folks that developed open hardware, like CAD designs for cold atoms, and also supporting with hackathons and connecting the community. And we're also partnering in Waterloo with the Open Quantum Design, which is fully open source ion-based quantum computer. Also, let me mention that we are really glad to support this USLA students quantum device workshop. I think it's the first really open hardware event focused on superconducting qubits. And there's also Michel Devoré somewhere here. And so really excited that we could like support this event that was so successful. And now finally to my last topic, which is community growth. So quantum computing needs a larger pool of talent and to continue to develop it. We need new tooling in the ecosystem. We need also folks to become more productive as technology advances and to learn about these other tools that are available. And I would say that all this community work is why Unitary Foundation exists, to really build a better open ecosystem in quantum technology. And open source, it's a way to right now do, to some extent, some research at scale, or at least without reinventing the wheel of every step. And so to focus on really what is the most productive part. And we're really mimicking what has happened in other parts of open source over the years, with the Linux Foundation, with the Wikimedia Foundation, and even with projects like Archive that we all, I imagine, cherish. They're all supported by some sort of like foundation backing them up for the common goods that they bring to the community. So Unitary Foundation really started with microgrants, $4,000, no strings attached, given to folks in the space. Right now, we're given to more than 120 teams in 34 countries. Then there's the technical staff that I lead, which performs research that we're best positioned to develop, such as UCC, Mythic, Metric. And then there's this like community. We have more than 5,000 folks joining our Discord server, and I invite you to join. Myself, I also started with QuTiP, so I needed to speak a little bit about it. It's not technically only quantum computing focused, but it's really one of the most successful projects in quantum optics for the simulation of realistic noise models in the system. And I also want you to point out there's this new QuTiP 5 paper that just came out and it's accepted for publication. Really gives you like a fresh overview of a project. You may know QuTiP, but you may know from many versions back. Of course, people use the master equation solver with Lindblad dissipators. But I think I have a couple of minutes. Yeah, but really there's so much more that has grown out of this ecosystem. There's even a quantum optics in Julia project, the quantum toolbox in Julia that is built out of QuTiP in Julia. And we also worked on the compiler level simulation at the pulse level, even with realistic pulses that are subject to all these very complex levels of noise. So I really encourage you to check out QuTiP and all its extension integrations, from JAX to Julia to really like low-level C optimization behind the hood. And I also want to talk about the impact of these microgrants, because as I mentioned, there's a lot of duplication in the space, but we need new tools. And also we need these tools to speak to each other. And just as I mentioned, like Jeff is an example of folks from different entities working together. I want to mention that Unitary Foundation gave a grant to Yao.jl, one of the first projects in Julia for developing algorithms, and PyZX, which really pioneered the use of ZZ calculus to optimize the compilation stack. And then these two projects sort of like learned about each other, and another grant was given to Yaolang, which is a domain-specific language that was inspired by PyZX, and eventually also served as an inspiration for Kirin. So you see that this kind of like support is really important. And also here, I think there's like some of the developers of Graphics, which is a really recent project in measurement-based quantum computing, an area that to some extent is a bit underdeveloped with respect to other kind of like compilations, and really optimal for photonics compilers. And as part of a European project, QLES, as Unitary Foundation, we're leveraging this sort of like tooling. So in this project, what we do, we start with a chemistry problem, we map it to VQE or VQAs, and then we make it run on photonics. And we just could have not done what we've done to date, thanks to the existence of tools like PySCF from the chemistry orbitals, OpenFermion, then Qiskit for the quantum circuits, and tools like Perceval by Candela that maps a quantum circuit to actually a linear optic with beam splitters on a table. And then thanks to that, we can then model tools from AFOS, a startup that makes these glass-made devices, and then also apply error mitigation with Mythic. If you want to be part of this Unitary Foundation community, please join it. We have a yearly hackathon running online. We have Quantum Wednesdays. We have a yearly meetup, UnitaryCon. Last year was together. This year was together with IEEE. And we also have the new survey coming up in a couple of weeks. About Quantum Wednesdays, I also want to mention, this is like on the Discord server, everyone can join. It's a bit late, C time, like 6:30 p.m. But really, you can see, these were the roster of upcoming invited speakers. And generally, these are talks focused on quantum software. And I should finish by thanking our supporters, core members, supporters members. We just had Orange QS coming on board, supporting and donating to what we do. And also I want to mention, I don't know if this has been announced yet, but really glad that the Mozilla Foundation is also supporting us. So I think that it's important that we start to look more, integrate more with the open source ecosystem beyond quantum. And finally, last but not least, let me thank really the team at Unitary Foundation for all the work they've been doing. Thank you very much.
Thank you.